Hi, my name is Camille and welcome to the Top G Tutors channel, and this is the beginning of my new AP Physics 1 course. I also have plans to create AP Physics 2 course in future, and maybe in the end we'll have some kind of comprehensive general physics playlist. We'll see, okay? Now we shall start. And before we step into the world of physics, we have to make sure that everybody is good at significant figures, and there's no such people who've never heard about scientific notation, and of course that you can easily work with SI units. So that's why in this episode we're covering the holy trinity of physics communication: significant figures, scientific notation, and the SI units. This is the essential math toolkit that makes our calculations clean and our answers precise. So let's get started. Alright, we'll start with significant figures, or Sig Figs, yeah, if you want to sound cool in the lab. So what are they actually? They're basically the digits in some measurement that makes that tell us how precise that measurement is. Yeah, I know. Here's an easy way to think about it. For instance, if I say that I'm 6 feet tall, that's one level of precision. But if I say that I'm 6.002 feet tall, for example, and now I'm trying to convince you that I know my height so precisely, it's like we're measuring me down to the millimeter. And that extra detail tells you I used a way more precise tool here. That's what significant figures do. They carry meaning. Now the tricky part, figuring out which digits are significant. And zeros in particular really like to play games with us. So let's start with the first number. And I want you to remember, once and for all, non-zero digits are significant always in all situations. That's all done. Thus, in this case, we have at least 1, 2, 3 Sig Figs, yeah? And what about zeros? So here it comes, 3 important rules about zeros. First one tells us that leading zeros don't count, and it's absolutely correct. You can think of them as some kind of placeholders, and as a result, for this number, correct answer is gonna be 3. Okay, let's move on to trailing zeros, and they're actually sneaky. We have to keep in mind that in this case, everything depends on decimal point. If there is no decimal point, trailing zeros aren't significant. That's why in second number we have only 3 Sig Figs. However, it turns out if I do put point here, yeah, the number of significant figures is 5 now. So if there is a decimal point, zeros in the end are significant. I also have to mention that you can see sometimes this number written like that. And actually, yes, you can put a bar over the top, and that's another way to indicate that a zero is significant. Therefore, third number, yeah, will also have 5 Sig Figs. So yeah, decimals can make or break your zeros. And the last one, zeros between non-zero digits are significant. Easy. That the right answer here is 5 Sig Figs. Okay, let's test this. How many Sig Figs in this number? And correct answer is going to be 3. The 2 zeros count in the end and the 2. That's all. Okay, knowing how to count Sig Figs is step 1. Step 2 is how do we keep them when we do math. And here we have 2 different rules. If we talk about multiplication or division, your answer should have the same number of Sig Figs as the least precise number. And if we talk about addition or subtraction, your answer should have the same number of decimal places as the least precise number. And I find these rules very logical. Let's say you are calculating the area of a phone screen, yeah? You measure the length with a super precise caliper and you get, for example, 12.34 centimeters, yeah? Its length. But you measure the width with the basic ruler that only has centimeter marks, so you get, for example, 5.6 centimeters. Now, when you multiply them, your calculator spits out, for example, we'll see, 69.104 like this, okay, But it would be ridiculous to say that area is 69.104 centimeters squared. Yeah. Why? Because your width measurement, 5.6 centimeters, is fuzzy. That 6 is an estimate. It could be 5.55 or 5.64, and that fuzziness gets multiplied into your answer. So the rule forces us to round to 2 Sig Figs, because the least precise number here is 5.6 and it has only 2 Sig Figs. So the correct answer is gonna be 69 centimeters squared. And okay, if we talk about addition, or imagine you have a precise digital scale, yeah, telling you a beaker weight. And for example, it tells you it's 120.55 grams, yeah. You add a chemical that you weighed on an old scale that only shows grams. So you write down 5 grams, for example. And the total isn't 125.55 grams. No, that's not correct. The chemical's mass is the weak point. It could be 4.6 or 5.4 grams. That uncertainty swamps the precise decimals from the beaker's weight. So we round the total to the nearest gram. And that's why the final answer is gonna be 126 grams. The rule prevents us from pretending we know more than we actually do. Okay, let's look at more examples. Yeah. For example, let's multiply 2.34 by 1.2. And so let's use our calculator. And calculator tells me that I have here 2.808. But again, 2.34 has 3 Sig Figs. 1.2 has 2 Sig Figs. So the answer should have 2 Sig Figs. So we have to round it up to 2 Sig Figs. Not up, yeah, just 2 Sig Figs. We will not round it to here up. So the final answer is going to be 2.8. Easy. Let's take one more example with addition. Let's add 2, 12, for example, 118. And let's say 0.03. And again, we want to write this. That final answers have to be 12.1, I think, yeah, 43. Yes, of course. But again, 0.03 has only 2 decimal places. So we round the result to 2 decimal places. And we get 12.14 here. Okay, and what we've got some little more complex calculation that involves some addition, subtraction, some multiplication, division. No trouble. The key is to follow the exact same order of operation as you always do when calculating, and apply the Sig Fig rule at the end of each step. For instance, let's calculate this. 6.3 plus 7.12 divided by 1.231. And so the step 1 is to add 6.3 and 7.12. And here we go, we have 3, the answer is gonna be 13.4. That's all. Why? Because the least precise number here has only 1 decimal place. So this is the correct answer. Then we have to do division here. And we divide 13.4 by 1.231. And we get, let's see. So my calculator gives me 10.88 here and 5. It doesn't matter. So, and we understand that the least precise number here is 13.4 and it has only 3 Sig Figs, so our final answer should have also 3 Sig Figs, and we have to round up this answer to 10.9. That's all. Now that Sig Figs are under control, let's talk about scientific notation. Have you ever noticed how numbers in science can get kind of ridiculous? Like, you see that one number that's this, yeah, 0.000000045, and another that's this, that's called Avogadro's number That's a lot of zeros to count, and honestly, no one has time for that. So scientists came up with a shortcut, scientific notation. You know, in life, usually a shortcut is not such a good thing. No shortcuts, yeah, only hard work. Yeah, alright, everything is very simple. Here is the rule. We write numbers as 1 and 0 digit to the left of the decimal point times 10 to some power. For example, Avogadro's number will look like this. 6.02 times 10 to the power of 23. And the second number is gonna be 4.5 times 10 to the power of minus negative 7. And think of the exponent as how many places you move the decimal point. So a positive exponent tells you to move the decimal point to the right, making the number bigger. Yeah, so we move the decimal point to the right. Okay, and a negative exponent tells you to move it to the left, making the number smaller. So let's take a number like 52,300. Writing all those zeros is messy and it's easy to miscount, so we use scientific notation. We find the significant digits, and they are here 5.23, and then ask how many places did I move the decimal point to get from 5.23 back to 52,300. And the decimal point moves 4 places to the right. Yeah. So 52,300 becomes 5.23 times 10 to the power of 4, again because we moved it 4 places to the right. So why is this so useful? First, it keeps things neat. No one wants to count 15 zeros every time. It makes math easy. You can break the problem into 2 simple parts: the numbers and the exponents. For example, yeah, let's calculate this. 10 times 2 times 10 to the power of, let's see, 3, multiplied by 3 times 10 to the power of 4. Yeah, and first you multiply the numbers. 2 times 3 and we get 6. Then we add the exponents. 3 plus 4, we get 7. Done! The answer is 6 times 10 to the power of 7. That's all. And here's a little trick. When you write a number scientific notation, the digits you include show your Sig Figs. Yeah, for example, the number that's written like that, 4.50 times 10 to the power of 2, has 3 Sig Figs. And number 4.5 times 10 to the power of 2 has 2 Sig Figs. So see how scientific notation and Sig Figs actually work together. Let's do a quick challenge. Let's write these numbers in scientific notation. Yeah, 0.003120. And first we see that it has 4 Sig Figs. Yeah, 3 non-zero digits and 1 trailing 0, but we have decimal points, so it also is significant. Okay, step 1, move the decimal so there's just 1 non-zero digit on the left, and that gives us 3.120. Yep. So step 2, count how many places you moved it. That's 4 places, so the power is -4. Okay, final answer. So final answer is gonna be 3.128 times 10 to the power of -4. Boom, 2 birds, 1 stone. Okay, last piece of puzzle, SI units. SI stands for System International. Yeah, okay, the International System of Units is basically the agreed upon language of measurement in science. Without it, physics would be chaos. Imagine I measure distance using my own unit that's called, of course, Camille, and you are shocked. Of course, because it appears you prefer to use furlongs. So the SI system keeps us all on the same page. Here are the 7 base SI units you will need for AP Physics. Yeah, and meters, kilograms, seconds, ampere, Kelvin, mole, and candela. And actually, candela is rare in physics problems, but still official. But I don't really believe you will use them. But from this, we can build all other units. For example, yeah, speed. We know that speed is measured in meters per second. easy. Okay, what about force? Yeah, for instance, force. We know that force is measured in newtons, you would say. But newtons, we call newton a kilogram, in fact, times meters per second squared. So again, we can build Newton, Newton using these base units. So honestly, yeah, in near future, you will use only first three of them: meters, kilograms, and seconds. And because we will talk only about kinematics and dynamics in near future. So the SI system uses prefixes to handle very large and very small numbers, which is incredibly useful. Here are the most common ones you will see: giga, mega, kilo, centi, milli, micro, nano, pico. And actually, yeah, I've written the most popular ones. And for example, giga, I think you've heard about it when some IT specialists talk about gigabytes, etc. And now you might see this list and think, okay, more definitions to memorize, but their purpose is actually rooted in efficiency. Why write a bunch of zeros when you don't have to? Let's say you have 5 million to 200,000 joules, yeah, and of some energy. Your first thought is probably, that's too many zeros to write and read as easily. So you would use scientific notation, yeah, and you get 5.2 times 10 to the power of 6 joules. But we can make it even more convenient by using a prefix. Since mega means 10 to the power of 6, we can simply write this as 5.2 megajoules. And it's cleaner, faster, and harder to misinterpret. That's the real power of these prefixes. That they are not just definitions, they are shortcuts, clarity. Let's look at the basic examples again with this in mind. Yeah, for example, let's convert 9 kilometers to meters. And again, kilo means 10 to the power of 3, so we will have 9,000 meters. Very easy. Okay, now for example, let's convert for 13 milliseconds, yeah, to seconds. And we can again see that milli means 10 to the power of -3, so we'll have 0.013 milliseconds. Now, here is the tool that makes conversion painless: dimensional analysis, or the factor label method. Think of it as a game of unit Jenga, yeah, but instead of making the tower fall, you're strategically pulling out units until you're left with the one you want. The idea is very simple. You multiply by fractions that are cleverly disguised versions of 1. Let's look at the examples. For example, let's convert 2,500 millimeters to meters. Yeah. And step 1, of course, to write it down. Step 2 is multiply by the conversion factor. And again, you want to get meters in the end, so you have to make sure that the millimeters are in the denominator, and because you want to cancel the millimeters in the numerator, and the fraction is gonna be 1 meter divided by 1,000 millimeters. And why? Because it also has to be exactly equal to 1, so, and we know that 1 meter is 1,000 millimeters, so our conversion factor is gonna be like this. And the millimeter cancel out, leaving you with 2.5 meters. That's all done. Let's do another with kilometers per hour. Yeah, let's convert 60 kilometers per hour to meters per second. And we'll start with kilometers. We'll multiply by conversion factor 1,000 meters divided by 1 kilometer. And why again? Because we want to cancel the kilometers, so the kilometers are in the denominator, and we have to make it equal, top and the bottom. Yeah, we have to make them equal. So on the top we need 1,000 meters, because 1 kilometer equals 1,000 meters. And here we will have 60,000 meters per hour. Okay, next is time. We have to multiply it by, now 1 hour divided by 3,600 seconds. Again, to cancel hours, yeah, and that's why. But we know that in 1 hour we have 3,600 seconds, and in the end we get hours cancel out, and we get 60,000, yeah, divided by 3,600, and we get, my calculator gives me 16.67. But we know that we had only 60 kilometers per hour in the beginning, yeah. Conversion factors, we don't have to include them. We have to think only about the input. So we had only 60 kilometers per hour, and it has only one sig fig. That's why our final answer also should have one sig fig. So we have to round it to one sig fig, and we'll have 20 meters per second. Again, but why conversion factors are, we don't have to think about conversion factors, yeah, when we try to count the number of sig figs. Of course, because they are, they're infinitely exact numbers. So 1 hour, it's not just one, it's 1.00000 in many zeros, and they have infinity sig figs, a lot of sig figs. So we don't have to mind about that at all. Now let's tackle an American classic, miles per hour to meters per second. And this is a perfect example because you will see it all the time in physics. Example, yeah, convert 65 miles per hour to meters per second. And we know we need to convert miles, meters, and hours and seconds. We can do this in one line, no problem. Yeah, and we know 1 mile is 1609 meters. So to cancel miles, we put that in a fraction with miles in the denominator, of course, and we'll have 1609 meters on the top and 1 mile on the bottom. So now we have 65 miles, yeah, per hour times 1609 divided by 1 meter, 1 mile, and meters on the top. And of course, miles cancel out, and we will have 65 times 1609 meters per hour. And now the last step is to convert hours to seconds, yeah, and so we have to multiply this by conversion factor. We already know it. It's 1 divided by 3,600. Hours on the top and seconds on the bottom. So seconds cancel out, hours cancel out, and we get an of course, this is my mistake. Hours on the we need now to cancel hours. Yeah, everything was good actually. Yes. So we cancel hours, and we get in the end, we will see now, 29,005 meters per second. And again, we had in the beginning, yeah, we had only 2 sig figs, so our final answer also should have 2 sig figs. So we round it to 2 sig figs, and the final answer is gonna be 29 meters per second. Alright, let's wrap this up. We covered 3 essential tools today. Significant figures tell us how precise our measurements are. Scientific notation keeps numbers manageable, especially huge or tiny ones. SI units gives us universal system of measurements plus the fractal label method to switch between them. And master this, and you will have the foundation you will need for every physics calculation in AP Physics 1. And hey, if this lesson helped you, don't forget to hit that like button and subscribe. It really helps the channel to grow and lets me know you're enjoying the series. Thanks for watching. I'll see you in the next lesson.